Hello everyone. So today I'm going to teach you about a circuit analysis technique called nodal analysis. Essentially, it is a very systematic way of applying Kirchhoff's current law, and it can really simplify more complex circuits. All the circuits that you'll be dealing with in this course can be solved using KVL, KCL loops, and Ohm's law. But the reality is that as circuits get more complex, adding additional tools and methods of analysis that are ultimately based on those three laws is going to be really helpful for you. So what I'm going to do is I'm going to start off with a very basic example and walk you through the steps of nodal analysis. So let's say we have the following circuit. We have a current source, I'll call that IS1, and then we have a resistor, call it R1, and then we have two resistors in series, R2 and R3. And then we have another current source, I'll call it IS2, and then another resistor, I'll call it I4. And essentially, let's say that we want to solve for all the voltages and currents in this circuit given these known values for the current sources and the resistances. Now again, as I mentioned, you could just apply KVL and KCL a bunch of times and you could do it, it just would be less systematic. So let me show you a better way. So the nodal steps for nodal analysis is number one, add a ground or reference node. So in this schematic, we have three nodes, right? And essentially you want to add a ground to one of them. This is the symbol for ground. I'm going just to add it to the lowest one because that's just more intuitive, like ground is lower, so I'm just going to add it there, but we could have added it anywhere and any one of the nodes, and that would have been just fine. Now, let me just make sure everyone's clear on what a node actually is, or I'm sorry, not a node, a ground is. Essentially, it's like your reference point for measuring voltages. Kind of like back to our water analogy with the two tanks with a different height. You could say that like the ground or the lowest height is that's like your reference point, right? And then any tanks that are higher than that, you can measure their height based on a certain reference point. Remember that voltage is always about a difference in potential energy between 2 points. So essentially, when we put that ground symbol, we're saying we're defining this as the arbitrary point as being 0 volts. We're just going to say that's 0 volts. Just like if you're talking about potential energy, like gravitational potential energy, I could define the level here as the height equals 0 point, and then anything higher um, above that, it's measured with respect to this. Or I could define my height with respect to the ground, the actual physical ground beneath me. And so essentially it's like a reference point. Anytime you're talking about stored potential energy, you have to designate a reference point. The cool thing about nodal analysis is that it doesn't matter what you pick as your reference point, just so long as you pick one and you're consistent in your equations. So I think it's more consistent just to stick it on the bottom, more intuitive. So I think it's definitely more intuitive. So I'm going to stick it there. And then after that, next step is label nodes and voltages. So let's label all of our nodes here. So we've got a node here, all of them besides the ground node. Then we have a node here. So I'll call that node 1. This is node 2. All right. Now we also want to define our nodal voltages. We'll call this one V1 and this one V2. So in nodal analysis, oftentimes we'll talk about how, the voltage at V1 or at node 1 is such and such. And you know that voltage is always about a difference between 2 points. You can never just say, oh, the voltage at a point. But in nodal analysis, if we say, oh, the voltage at this point, we mean the voltage between that node and the ground. So if you had a multimeter or like a voltmeter to measure the voltage, you stick it at the node and then on the ground pin there, because that's like your reference point there. So so once we've done that, you label your nodes and your voltages there. Then the third step is to apply KCL to each node. Okay, so let's go ahead and do that then. So node 1, KCL states that the sum of the currents going into a node is equal to 0. So let's go through all of our currents that are going into the node. We have IS1 just going into node 1. So IS1, then plus the current going into the node here. And yeah, actually, so I'm gonna go ahead, you can go ahead and just define currents if they're not labeled. So I'm gonna label this one IR1, and then this one actually I could just call this I1. That's easier. And then I2, 3. So you can go ahead and label your currents. The direction doesn't matter. Again, the math will all work out. You just have to be consistent. So going back to our node here, we've got IS1 plus we want the current going into the node here. But the way I drew this is the current's going out of the nodes. That means we have to negate it. It has to be minus I1. So the current going into the node here is minus I1. So minus I1. And then we want the current going into the node from this branch as well. And we have this oriented this direction. So that means it would be minus I23 that's actually going into the node. So plus minus I23, and that's all equal to 0. And then we want node 2. So let's do node 2. Current going in, IS2, plus current going in, I23 is going in, and it's automatic, it's already oriented as going in, so we don't need to negate it. We just do plus I23. Then plus the current going in here. Oh, I forgot to define the direction here. Again, it can be whatever direction we want. I'll just call it I4. So the current going through R4. So I happen to draw it as going out, so that means we want the current going in, right? We're summing currents going in, so minus I4 is going to be the term here. Minus I4 is equal to 0. So there are the equations. We've applied KCL. And it doesn't matter how complex the circuit is. If we had a bunch of other nodes, you just do that to all the other nodes and you get a bunch of these equations.
Hey, Miwa. Are you the therapy cat for the students? Are you? Are you the therapy cat? Yeah? Yeah, yes you are.
Then the fourth step is apply Ohm's law to each KCL equation. So let me give you an example. So for node 1, the KCL equation with node 1. Here we've got the sum of all of our terms here, IS1, I1, and I23. We can express I1 and I23 in terms of the nodal voltages using Ohm's law. So I1, if we go back to our circuit here, I1 is equal to V1 divided by R1 because the voltage across it is V1, our nodal voltage is across R1, so V1 divided by R1 will give us I1. So I1 is equal to V1 divided by R1. And then the other current we have, I23. This one you have to think about a little bit more, but essentially that current would be the voltage across these two resistors divided by their total resistance. We know the total resistance is R2 plus R3, but the voltage here, what you have to do, remember that a voltage is about a difference in potential energy, right? Or a difference in height. So the voltage across these resistors in terms of your nodal voltages is V1 minus V2. V1 minus V2 gives you that potential difference across the resistors. So I23 equals V1 minus V2 over the sum of R2 plus R3. And it's important that we did V1 minus V2. If we had defined the current as going the other direction, then you'd want to do V2 minus V1. So we've got our two expressions there. Let's do the same thing for node 2. So for node 2, we want, we already have I23. We know what I23 is. We came up with an expression for that. IS2 is given. So what is I4 based on the voltages? Well, V2, we have a voltage V2 across R4. So I4 is going to be V2 divided by R4. So I2 is going to be equal to V2 over R4. So then what you can do is you can take these values and plug them into these equations. And essentially what you then have is you have two equations and you have two unknowns, which is your nodal voltages V1 and V2. So I'm not going to go through all the steps, but if you plug those in and do a bit of algebra, you can arrive at the following expression for your equations here. It'll be minus 1 over R1 plus 1 over R2 plus R3 times v1 plus 1 over r2 plus r3 times v2, and that's going to be equal to minus is1. I was just kind of doing a lot of simplification, and I'd recommend you put your equations in this form where you have all the variables you're solving for on one side of the equation and then constants on the other side. And that's from the node 1 equation. And then the other equation, when you do that, plug that in, you'll get um, 1 over r2 plus r3 times v1 minus 1 over r2 plus r3 plus 1 over r4 v2, and that's all going to be equal to minus is2. So once you have your equations in this form, you can then express them in matrix form to solve the equations. And that's just a really systematic way of solving them, especially as you get more complex circuits. Doing this and then solving it in a matrix is really nice and systematic, and you can use like a calculator to just automatically solve for all of your unknowns. So the matrix equation would then look like this. Have So once you get your equation in this matrix form, you can then use mathematical techniques to solve for this. And the cool thing is that this is just a very systematic way of doing that. So that pretty much summarizes nodal analysis. And in the next video, I'll cover the topic of supernodes. But for now, this gives a good overview of the technique. I hope that was helpful. Thanks for watching, and I'll see you next time. Hello, everybody. Thanks for watching. If you found this content helpful, would you please consider liking and subscribing to the channel? That will help other people find it. And if you won't do it for me, will you do it for my cat, Muon? Named after my favorite subatomic particle, by the way. So, she will be very, very upset if you do not like and subscribe. So please, don't disappoint. How could you say no to this cuteness?